So let's do one quick filter example with numbers since we haven't seen one yet. So let's say we have a filter that looks like this, and our resistance is 1 kilo ohm and our capacitance is 0.5 microfarads. So if we wanted to characterize what this filter does, first we can see if it's a high pass or low pass. So the capacitor is connected to ground, which means we're measuring across the capacitor, which is going to have a, let's see, a small impedance at high frequencies, which means that at high frequencies our gain is going to be close to 0. So this must be a low pass filter. We can find the 3 dB point, omega 3 dB, because that is equal to 1 over RC. So that's 1 over 1,000 times 0.5 times 10 to the minus 6th. This gives me 2,000 radians per second, or a 3 dB frequency of 2,000 over 2 pi, which is equal to 318 hertz. So without really knowing anything more, we can draw a rough estimate of what the frequency response of this filter looks like. So it's a low pass, so it's 1 on this side, and it goes down like this. And where this is 70% of the max, this is our 318 hertz, the 3 dB point. All right, and if we wanted to calculate the gain at a particular frequency and figure out the response to some signal, we could definitely do that. Okay, speaking of figuring out responses to some signal, all this filter business has been assuming that we're putting in a single frequency into our filter and measuring the response of it to that single frequency. Why is that useful? Because it seems like lots of signals we have in electronics or communications or music, these are not pure sine waves. If you've ever looked at something like this on an oscilloscope or a similar tool, you see that they are very complicated looking waveforms. But it turns out this French physicist named Joseph Fourier realized that any arbitrary waveform, any arbitrary function you can come up with, you can express as a sum of sine waves at different frequencies and with potentially different phases as well. So what this means is that you can take, well, let's draw a little picture here. And this relies on the linearity of our circuits, meaning that the output is always proportional to the input. And if you do put in a sine wave, you always get out a sine wave at the same frequency. That's a property of all of our circuits that we've talked about so far. So let's imagine we have a complicated signal. Fourier says we can split it into its frequency components. So this we can kind of think of as a few different pieces. And how to do this is math that is not particularly complicated, but it is kind of advanced to understand. And then we think about the response of our filter to each of these frequencies individually. So, there's a component at 100 hertz and 500 hertz and 232 hertz or whatever. And this might be 1,000 different frequency components or something, depending on how you analyze the signal. Anyway, so you can analyze each one of these using the gain of the filter at that frequency easily. And also, if you know how it changes the phase, you should include that information too. And then you have all of these changed frequency components that now have different amplitudes than they started. So over here, each of these has some V in, right? Over here, each of these has some V out. And these are not the same, but we can calculate what these are using the properties of our filter. Then, to get our signal back, all we have to do is add these together, and we get our output signal for anything that we put into this filter. So this is kind of a little look at why these filters, why this analysis of the filters is so useful, because the gain at these different frequencies doesn't just tell us about sine waves, it tells us about everything you can put into the filter. Okay, so Last, I wanted to talk about some applications of different sorts of filters. So, so for example, if we have a low pass filter, you could use this, for example, let's say you have a power supply, like a wall voltage power supply that's oscillating at 60 hertz. And there's a whole bunch of static on it because there's some old piece of equipment that is janky and causes these like voltage spikes. Spikes will always have high frequency components to them. So you could use a low pass filter on this to remove noise or spikes from your 60 hertz power. So this is effectively like cleaning the power signal. So these noises and spikes don't interfere with something you have plugged into the wall. You're allowing the 60 hertz through, but you're not allowing higher frequency components through because you don't want those. You could also use this to separate out low frequencies from an electronic audio signal and send just those low frequencies to some kind of speaker that's good at those low frequencies, what we would call a woofer or a subwoofer. If you try to send high frequencies to a speaker designed for low frequencies, you get buzzes and weird stuff happening. So in general, you only want the low frequencies to go to the low frequency speakers, and then you have little high frequency speakers that are good at high frequencies, and you can use a high pass filter to send the high frequencies to that. So this is how stereo systems work, at least in some simple way. Other applications that just come to mind, band stop filters are very useful because if you have some signal component that you don't want, you can remove it. So for example, 60 hertz is great when you want to plug something into it, but if you're making a sensitive measurement, a circuit can actually couple to the magnetic field that's caused by oscillating currents at 60 hertz, which are pretty much everywhere. And so this band stop filter, you can use, let's say I'm doing some sensitive measurement and I'm just seeing this 60 hertz signal on everything because my circuit's acting like a little antenna. I can apply a filter to that signal to just remove the 60 hertz, plus or minus 1 hertz. And the effect of that is that everything else stays the same. The gain is 1, but just around here, that disappears from the signal. So that's super useful. You'll also see stuff like this in audio. 60 hertz or 120 hertz filter in like stereo amplifiers is really common because hum at that frequency is a similar problem to what I just described because it's some sensitive signal that you're amplifying really big, and that can be affected by the 60 hertz wall voltage. So yeah, these are a few applications we have. I said this was last, but there is one more thing I want to talk about, and that is talking about decibels again. So remember, and I'm just going to do a little quick example. For a low pass filter, at high frequencies, at high enough frequencies, our gain looked like 1 over omega RC. Okay, so if we were to write an expression for gain in decibels, it's equal to 20 times the log of 1 over omega RC. Well, if you remember your logs, a multiplying constant like RC, these are constants, right? Just is a number that gets added outside the log. So this looks like the log of 1 over omega plus some constant that we don't really care about. Excuse me. The log of 1 over something is equal to the minus log of something. So this is minus 20 log of omega. And so this describes how our gain decreases with increasing frequency. And note that if so this log is the base 10 log. So if omega goes up by a factor of 10, our gain goes down by a factor of 10. And if omega goes up by a factor of 10, our gain in decibels is minus 20. So each time our frequency goes up by a factor of 10, our gain goes down by 20 decibels, 20, 40, 60, etc. So this means on a log, if we plot on a logarithmic scale the frequency versus the gain in dB, for a low pass filter, we see something that looks like this. We see this linear behavior, and the slope of this line is minus 20 decibels. That is like, the rise over the decade, one factor of 10 in the frequency. So 20 dB per decade is the slope of the filters, the slope of all of the filters we've talked about: low pass, high pass, and band pass.